Thank you, Patrick. Yeah, so very, very happy to be here. Thank you for inviting me. I'm going to talk about consensus, but I'm actually going to surprise you and start with a retrospective. Yeah, so three things. I'm going to start with a little bit of hindsight because it's 2020 this year, and go back to 2016. This is the first IC3 retreat that I physically attended, and so I'm going to go back there and see what have we done the last 4 years. Then I'm going to talk about finance, in particular focus on fairness and fairness through anonymity, and then talk about consensus and, as I promised, about asynchrony, synchrony, and partial synchrony. So I want you all to kind of close your eyes and imagine that this is not 2020 anymore, but we're actually going back 4 years to May 2016. So just to remind everyone, this is the first IC3 retreat in New York City. I think there are several people here that were in this retreat, that I remember seeing them. Yeah, so just if you don't remember, so Bitcoin was about $500 at that time. So in hindsight, you would get 20x just by investing in Bitcoin. The hash rate of Bitcoin was about 1 exahash. I think today it's about more than 100 exahash. So hash rate increased 100x wise. And ETH was about $10. So I think, again, in hindsight, you would get 30x on your investment if that's what you did back in 2016. And even back then in 2016, blockchain there was a lot of hype around it, and the keynote was given by Ari, and I actually found his slides. They're available online, and even at that time, there was a lot of discussion about the promise of blockchain. And Ari was very smart, so he basically said, instead of saying what I'm going to promise that I'm going to do, here's things that I'm promising that blockchain will not do. And so I want to now go over and check whether the things that Ari promised blockchain will not do, indeed, we didn't do by mistake. So Ari promised that blockchain will not reverse aging, and indeed, I think we didn't manage to reverse aging. Ari promised that blockchain will not bring peace to the Middle East, and yeah, I think 4 years later, he was spot on. He actually also promised that blockchain will not save the Republican Party, and so I'll let you all decide whether he succeeded in that or not. I was also invited to give a very short talk in 2016, and I wasn't as smart as Ari, so I actually I talked about things that I do think will happen, and so one of the things that we said at the time is that we believe that the focus of blockchain is on disrupting the financial world. It wasn't about supply chain or IoT or machine learning. It was really about the financial world, and I think in that sense, hindsight in 2020, this was pretty correct, at least in the last 4 years. We're seeing that the major focus of blockchain is in the financial world. We also kind of had a technical view about how these technologies look like. How does a blockchain stack look like? And we had this layered view. And as you know, when you think about complex systems, if you can build clean abstractions, it helps you understand this technology in a better way. And so we presented this slide in 2016, talking about kind of the 3 layers. The bottom layer is the ledger, the blockchain core. We talked about Byzantine agreement and proof of work. The middle layer is smart contracts. And the top layer are these services or applications that are built on top of smart contracts. And at least my feeling is that this layered view of what a blockchain technology is actually a pretty good abstraction of many systems in this space. We also had kind of a technical vision about what we plan to focus on the next 4 years. We said we're going to focus on permissioned private blockchains, on high throughput Byzantine agreement. Back in 2016, there was only Bitcoin and maybe Ethereum was just arriving, but we already said there's going to be many ledgers. I think that was also a pretty good prediction. We talked about the importance of cross-ledger transactions, And I think this decentralized finance is a good example of why this is so important. And we also talked about technical abilities of reconfiguration and changing the focus. And so, in the last 4 years, VMware has been working quite considerably in this space, but we definitely weren't the loudest, and we haven't been speaking a lot about what we're doing. There was no public hearings in Congress that VMware was involved in. You didn't see any press releases about the future things that VMware will build. So we've been pretty quiet, but behind the scenes, we've been building a lot of work, both in the design and in software and in business around blockchain and decentralized trust infrastructure. So today we have a world-class research group. By the way, we're always hiring and we're always open to collaboration. There's a large and rapidly growing blockchain business unit inside VMware. And we have major financial institutions which are co-innovating it with us and having joint projects with us. And again, these are kind of critical infrastructure projects, not proof of concepts. Finally, there's an open source GitHub, which I encourage you all to go and look at. This is Project Concord. And VMware is committed to a collaborative, open source, enterprise-grade blockchain infrastructure. So with this, I want to start the second part, which is a focus on fairness. And if I had to say, what is the kind of big challenge that I see, not just in this space, but in general for us as a society, this is in this notion of fairness. And here I gave one definition, which is to be impartial and just in treatment and behavior, without favorism or without discrimination. And so in particular, when we look at finance, we see a lot of challenges with fairness, and in particular with unfairness and in this decentralized finance world. So examples are power asymmetry. So for example, a lot of problems of front running, where some players have more power to do front running than others. We're all seeing the same thing in terms of who is allowed to invest early or earlier than others. And this is kind of this IPO and ICO movements. And more generally, there's this challenge of information asymmetry, where some parties simply know and have more information, and they can use this information to discriminate, to get better financial outcomes for their favor. And if you think about fairness and information asymmetry, then at a fundamental level, you're basically forced with two choices. There's not a lot you can do. So the first thing you can do is basically keep everything private and anonymous. So if everything is completely private and everything is anonymous, then nobody knows who is transacting. And so you get this complete fairness because you cannot be tagged by any information. So this gives you kind of a very strong ability. And part of the advantages of anonymity is that it gives you better fairness. Unfortunately, some of the things can't be private, and so the next best option is to make everything open, transparent, and accessible. And so this is kind of the public option, where since everybody can see everything, again, you reduce the amount of information asymmetry, and thereby increase fairness. And the technical challenge that we see here is really this transition from things that are completely private to things that are completely public. And there are many use cases where in the end you have some private decision that you want to make, but when you actually commit and make this decision becomes public and everybody can see it. And this is the challenge of, for example, front running, where there's this transition from a private decision to a public outcome or a public announcement. And what you like from a technical perspective is to actually do this in a fair manner. So this transition from private to public is done in a fair manner with a strong degree of privacy before it becomes public. In a technical perspective, I will focus on this abstraction called robust anonymous committed broadcasts. And what I will claim is that robust anonymous committed broadcast is kind of the foundation that allows you to transition from your private decisions to a public commitment of multiple decisions. And this is going to be the core of fairness. So what does it mean? Abstractly, there's kind of this ideal functionality. Clients send messages to the ideal functionality. And what the ideal functionality does is it takes all the messages it receives from the clients, it randomly permutes them, and it broadcasts a message showing all the messages from the clients. So here's kind of the property. So the first property of robust anonymous committed broadcast, it's robust in the sense that there's no way to block clients. This gives you the censorship resistance. The second property you'd like is anonymity, which is that nobody knows which client sent which message. All you know is that you have an anonymity set, a group of clients, and you can see what is the randomly permuted set of messages, but you cannot map back each message to each client. The third thing you want is this committed property, which basically means that once you send these messages, you can't roll back and change the message after the fact. And again, this is important if you're doing financial transactions and you want to make sure that everybody has a fair playing ground where they all commit to a message and then it all gets opened simultaneously. And finally, you want the end result to be broadcast in the sense that after there's kind of this random permutation, everybody learns about all the operations. And so this is this abstraction of robust anonymous committed broadcast. And if you're in this area, you know that secure multi-party computation protocols are the way to solve this problem. And typically the problem with MPC, with multi-party computation protocols, is that they are not scalable. So we're focusing also on this ability to scale robust anonymous committed broadcast. And so when I talk about scalability, I mean that it should work for hundreds of thousands to millions of clients in each iteration. So in each group of clients is hundreds or millions, and you could even imagine more. And this ideal functionality, well, ideal functionalities don't exist, but you can implement them just like you implement consensus protocols. You can implement them using multi-party computation. And we're envisioning tens or hundreds, and one day maybe thousands of servers that implement this functionality. And so two examples of work that they're trying to implement this type of abstraction of scalable, robust, anonymous committed broadcast is Honey Badger MPC. This was published in last CCS. And the second example is this upcoming paper with Avishai and Benny Pincus and myself, which is called Blinder, which again tries to implement this functionality. And I guess at a very high level, my point is that this scalable, robust, anonymous committed broadcast is a fundamental building block for obtaining fairness. It is the way in which you can transition from private client information to a publicly committed set of commands in such a way that the transition from private to public is done in a fair manner. And I believe that this is going to be a very important building block in the future. Yeah, so I'm going to transition now to the third part of the talk. And here I'm going to talk about the good, the bad, and the ugly. And this is going to be partial synchrony, synchrony, and asynchrony. And so these are not protocols. These are mathematical models of what we think the real world looks like. So in a sense, these are ways in which we model the world. And if we model the world in such a way, this then induces some protocol decisions. But really, this is kind of a meta decision about what is the right mathematical model to model the real world. And so, for those who want to have a very quick overview of what these definitions mean, so I'm going to say this in this slide. So in the asynchronous model, it's a very simple model. Any message sent between any two parties, the adversary can delay this message by any finite amount. So in particular, the message has to eventually arrive, but the adversary can delay this message by 1 second or 1 minute or even 1 hour or 1 year. So there's no upper bound on how much power the adversary has in terms of delaying messages. And again, these can be messages even between two non-faulty parties. So this is kind of the definition of the asynchronous model. In the synchronous model, there is some known upper bound delta. So let's imagine that delta is 10 seconds. And basically, what this model claims is that the power of the adversary is to delay any message, but it can only delay messages by at most 10 seconds. So it can choose to delay a message by half a second, or a third of a second, or 5 seconds, but no more than 10 seconds. And so this kind of limits the power of the adversary And so you could imagine that you might be able to have more or better functionalities under the synchronous model. The problem with this synchronous model is that you can imagine that under kind of a strong denial of service attack, then it could be that maybe messages take more than 10 seconds, or at least this is kind of what Dwork, Lynch, and Stockmeyer theorized in 1988 when they came with this very important paper about partial synchrony, where they defined this new notion of partial synchrony, which was kind of a compromise between asynchrony and synchrony. And so what this model basically said is that the system starts in asynchronous mode. So in the asynchronous mode, the adversary can just delay messages by any finite amount. But what the model said is that it made a promise. It said sometime, eventually, there will be some point in time, and they call this time GST, Global Stabilization Time. So it's an unknown point in time. You don't know when it will happen. It might happen 2 months from now, 2 weeks, 2 hours, or 2 seconds from now. Once this event happens, then the system becomes synchronous. So it really tries to capture a world where there are periods of asynchrony followed by a stabilization where the system is synchronous. And again, this has been a very successful notion in a lot of consensus protocols that kind of assume this partial synchrony model. And so I'm going to start with partial synchrony. And here, the gold standard is PBFT, Practical Byzantine Fault Tolerance. This is this work from the 1990s by Barbara Liskov. And this is the gold standard, I guess. And you will see a lot of different variants of this protocol, and I'll mention a few of them. But really, again, the idea here is that safety is maintained both in the asynchronous and synchronous phases. But liveness, the fact that you're making progress, is guaranteed only when the system is synchronous and only when there is a non-faulty leader. And in particular, when the system is synchronous and when there is a non-faulty leader, or maybe a quickly rotating set of non-faulty leaders, then you get very good throughput and very low latency. That's why people really like these systems. The big problem here is that when there's a faulty leader, even if there's no asynchrony, even when the system is already stabilized, with a faulty leader, no matter what you do, there's going to be some sort of view change hiccup. And this hiccup is going to cause several seconds of delay. And so this is kind of one of the big challenges in these systems is that, no matter how good they are, and here's kind of an example of some more recent ones, and they have very low communication complexity. They have a constant number of rounds per commitment. They use very small number of messages. But in the end, all these protocols suffer from this problem that a faulty leader will cause you kind of with a hiccup. So this is what I want to say today about partial synchrony. I think the main question here is whether people will be happy with this model of having taking the risk of a leader or a rotating leader that might kind of cause these performance hiccups. The second model I'd like to mention is Synchrony. This is kind of this model where there's a known upper bound on message delay. This is the typical model that people write, say, protocols in cryptography. But in distributed systems, in particular in the crash model, this is a model that basically was not used in industry. So we're seeing that starting, I guess, from the early 2000s, Google's, the Microsofts, the Facebooks, and all these big companies, and eventually everyone used state machine replication protocols in the crash failure model that used the partial synchrony model and not the synchronous model. So Synchrony was kind of an unsuccessful candidate. And really the problem here is that it gave you worse degree of safety, because if there was kind of a major denial of service, then it could cause disagreement and a fork. However, in the Byzantine model, it also gives you better safety, because there's kind of a fundamental gap where you can handle 1/2 Byzantine failures in the synchronous model and only 1/3 in the partial synchrony model. So I think in the Byzantine model, unlike the crash one, there's actually a big safety advantage for moving to the synchrony case. And I think the real change in mindset is the realization that protocols like Nakamoto consensus, this is kind of the consensus protocol that Bitcoin uses, and Ethereum and all those protocols built on proof of work, is a synchronous protocol. So it's based on synchrony. If you indeed imagine that if you could split the world into 2 parts that couldn't talk to each other, then potentially, Bitcoin could split into two different parts. And this led to a lot of research and innovation in, say, Nakamoto consensus on how to make sure that the world will not split into two different parts. For example, if you have many strong means of communication other than standard internet communication. And so here's kind of an example of recent work. Some of it is from a year ago, and some of it is from this work. At least the last three are works that I've been collaborating with Ling Ren and Kartik Nayak and other collaborators. And I think Kartik and Ling have been leading this effort of trying to get very practical synchronous protocols. And they've been working on this from, I guess, 2016. And this is kind of, I think, something that in last year really hit the optimal bounds for this synchronous setting. Finally, I want to mention the asynchronous model. And here, I guess, at least 4 years ago, the feeling was that these protocols are just too complicated. And so they're mainly theoretical interest. But I think there's a lot of recent advances. These advances are still in the systems and foundations perspective that now can allow us to imagine how asynchronous state machine replication could look and not be so ugly. So potentially there are elegant solutions. And I think that going forward, there's going to be a lot of interest in these asynchronous protocols. So to conclude, I kind of gave a retrospective about the retreat we had 4 years ago. And so, I want to ask, what will we say 4 years in the future in 2024 about 2020? And let's make sure that we are focusing on kind of the right problems. And in particular, I want to focus on two different aspects. One is, how do we handle fairness? What is the right technology to improve that? And the other is kind of interesting to see how will consensus protocols evolve, in particular, which models will kind of be more used relative to the others. So thank you.
We have time for one or two questions. If anyone in the audience has a question, you can put it in the Q&A box, or you can just unmute yourself. Oh, I don't think you can unmute yourself yet. So raise your hand if you want to ask a question. I mean, while we wait for one, I've got a question as well about fairness. So like the middle part of the talk, you mentioned that the ideal world is that there's a list of messages sent to an ideal functionality, and then they're randomly distributed out, or random order. So is fairness there the idea that given a set of people who send a transaction, the order should be, they don't have any control over the order of the transaction?
Yeah, so I think fairness is both in the fact that you cannot control the order, and also that it's simultaneous. So it's not the case that, let's say, maybe I can see your transaction and then decide what my transaction is.
Okay,
so this is kind of both. You're right. It's both about front-running prevention and also about kind of deciding a random order between everyone in a fair manner.
Okay, so I want to ask the opposite of that then. So what we sort of see in Ethereum today are these gas auctions. So what happens is that there's a smart contract, maybe there's an arbitrage moment, and you can make $100 if you get this trade, within the block. So what people are doing is that within the 14 seconds, they're trying to outbid each other in the gas market. And whoever outbids each other, gets in first and then gets, their transaction executed. But I want to ask, how does that compare to the fairness property? Because in a way, these bidders can pay up to $100 to get in, and they'll still make money. So is there any comparison of the fairness there? I mean, this is like the opposite scenario.
This is a great question. So I think what you're alluding to is kind of extending this to say that clients have to bid on entering, and maybe not everybody gets their transaction be part of this group or chosen, and only the highest bids. So you can build an auction mechanism on top of these functionalities. Yeah.
Okay, cool. That's all I wanted to ask. There's two more questions now. I'll just take these two. The first one's by Andrew. DeFi has so far not been cross-chain. Interested in your thoughts on what are the challenges and opportunities in cross-chain blockchains?
Yeah, that's a great question, and I actually don't have a very short one, but would you say that wrapped Bitcoins or wrapped tethers are not cross-chain, or are they cross-chain?
I would say wrapped Bitcoin. I mean, I guess it depends on your trust assumption. A lot of the wrapped Bitcoin so far has been trusted hardware in the middle. There's a project called TPTC that does have collateral locked up. Maybe Andrew, do you want to comment on that since you asked the question? Um, I don't know if he's typing or not, but I would count that as cross-chain.
So I would say these are examples of early ways to do cross-chain transactions. It's just like decentralized finance is still
Yeah.
mostly centralized, and we're slowly moving towards decentralization. I would say wrapped Bitcoin or wrapped tethers are examples of kind of slightly more centralized versions of eventually a decentralized future that we want to get to.
Okay. So what about just because he commented, what about the non-custodial protocols then, the decentralized ones? What do you think are the challenges so far?
Yeah, so I think the uh, the academic world has a lot of protocols that can handle um, two-phase commit type protocols that can make sure that you have consistency between different systems. The challenge in this world is that each one of these systems might have slightly different trust guarantees. So there's an arbitrage in the degree of trust that different systems have. And so I think combining the traditional classical two-phase commit type protocols with this understanding of different trust guarantees is kind of a frontier that hasn't been explored enough.